All right, the next phase we'll cover in digital is the venerable and ever so useful microprocessor. Now, what on earth is a microprocessor? A microprocessor is a huge collection of interconnected digital circuits, each of which perform a specific job, each of which you call into action with a program. Let me repeat that. A microprocessor is a microchip containing a huge collection of interconnected digital circuits, with each of those circuits performing a specific job, and you call each of those circuits into action with a program. The program is a series of instructions which you write. Each of those instructions will call upon the myriad of digital circuits you have at your disposal, all pre-built inside the microprocessor. So it is very versatile in that you have this bank of digital circuits pre-built for you, and you can activate each of those circuits as often or as seldom as you like. Now, typically these circuits will work with registers, either reading them or writing to them. Some of those registers will be connected to the outside of the chip, so you can use the registers to connect to the outside world. Sometimes the digital circuit you call to action could be, say, an analog to digital converter. Now, we'll get into these in more detail later on, but it's a very complex circuit that takes an analog voltage, measures it, and spits out a binary number, which represents how large or small that analog voltage is. Now, in any case, the CPU, or central processing unit, is a microchip containing a block of digital circuits which respond to a program. We saw what we called the clock line on our D-type flip-flop register. The clock is an essential part of the CPU. The clock sends out a continuous stream of pulses which trigger the functions of the CPU. For instance, there is a program counter which is just a register. But that register has an adjoined digital circuit which increments the number in the register by 1 every time it sees a clock pulse. The program counter is one of those digital circuits within the microprocessor. Now, the clock drives all functions of the CPU, causing it to step through your program. The program is stored in a series of memory locations, the program memory. An address bus goes to each of those memory locations. That address bus is driven by the program counter. So as the program counter counts up with each clock pulse, it keeps going through the program memory locations, so it goes through the program one line at a time. Each memory location stores one line of your program, your code. So let's say the program counter is at hexadecimal 0A. This goes down the address bus and connects memory location 0A to the data bus. Your program that you wrote was stored in the program memory. 0A would be the 10th line of your code, right? So let's say that line 10 of your program is hexadecimal A3. The reason you wrote that in there is because you wanted to activate the digital circuitry which is at address A3. So hexadecimal A3 gets dumped onto this data bus. There is another circuit which I'll call Fred. Fred, like everybody else in the microprocessor, is driven by the clock. Fred knows that this next line of the program is going to call upon one of the utility circuits. So Fred takes that A3 and dumps it onto the bus that controls all of the utility circuits. A3 goes down that bus, is demultiplexed, and triggers a register at address A3, which turns on the utility circuit at A3. I'll call that utility circuit Cindy. Cindy gets the call to go to work. The first thing she does is to tell Fred, hey, I need the next number in the program. It's going to be the data that I need. Cindy's sole purpose in life as a utility circuit is to take the next number in the program and to store that number in another register, which happens to be connected to 8 pins on the outside of the microchip. So Cindy waits for the next clock cycle, which triggers the program counter to count up 1, connecting the next memory location to send its stored number down the data bus. Fred didn't do anything because Cindy told him not to. So Cindy grabs that number. Cindy knows the specific address of the register, which is connected to those 8 pins going to the outside world. So she drops that address on the address bus and puts the number she snagged on another bus running throughout the whole CPU. Almost like sending mail, she just put the address onto the address bus, which gets demultiplexed on the other end, triggering the register to store the number that is now on the central data bus. That number happened to be binary 00010100, which is, what, 14 in hexadecimal? You put that number in. Well, why did you pick that number? Because in this particular instance, when you built this robot, you had these two pins in the microprocessor turning on two drive motors on your robot. Those two drive motors, one on each side of your trackmobile robot, drive the tracks forward. When you built all the circuitry, you connected those motors to these two pins on the microprocessor. By putting that number as the line in your program, you turned on those two motors, but not any other two motors or lights on your robot, which were connected to the other pins. If you had wanted to turn on the robot's headlights as well, you had them connected to pin 1. So you would have instead written in a binary number of 00010101 into your program. This would put a high on pin 1 as well, turning on the headlight control circuitry. Now, Cindy doesn't know this and she doesn't care. Her job is simply to take whatever number you gave her and send it to wherever you wanted that number sent. She's like the lady at the post office. She don't care what's in the letter. She just makes sure it gets delivered to the right address. So Cindy has now done her job. She now says to Fred, okay, I'm done now. And Cindy goes to sleep. Fred now knows that the next line in the program will be an instruction. It will be calling one of the many utility circuits you have available. The next clock pulse increments the program counter, sending the next line of your program down the data bus, which Fred grabs. He knows this is the address of one of the utility circuits, so he sends that number down the address bus controlling the utility circuits. It's demultiplexed at all of the utility circuits, but only one matches, of course. And that was the utility circuit whom I will call Clinton. So the signal wakes up Clinton. Clinton's job is a weird one, and it requires several steps. So Clinton gets the call to work and says to Fred, okay, Fred, I'm going to need the next number of the program, and then I'm going to be a while. So Fred waits for the next clock pulse and the next line in the program to get transmitted down the data bus. And then Fred actually pauses the program counter and then reads the paper or something for a while as Clinton does his work. Clinton's job is to get the next line in the program memory, which happens to be the address for a memory location. Clinton waits for that next number to come down the data bus. His circuitry grabs that number and drops it straight onto the central address bus in the heart of the CPU, which triggers a memory location to send the number it has stored down the central data bus of the CPU. Clinton has access to this central data bus, but Clinton, like everybody else in the CPU, is driven by the clock. The next clock pulse triggers him to grab that number off the data bus, load it into a special register he has in his circuitry. On the next clock pulse, his circuitry reads whatever number is in that register and turns it upside down. Every 1 is turned into a 0, and every 0 is turned into a 1. That's Clinton's job. That's what his circuitry does. The next clock pulse triggers Clinton's circuitry so that he sends that address he had before down the central address bus again, and he dumps the new converted number from his register down the central data bus right back to the memory location where he got the number. Clinton's job is now done. And so he wakes up Fred and says, yo, Fred, I'm done. And Clinton goes back to sleep. Fred now takes charge again, knowing that the next number to come out of the program is going to be the address of one of the utility circuits. So Fred is ready to pass your next instruction to the next utility circuit, of which they are all sitting there waiting to do your bidding. So you can see this loop of steps going on. Notice that some jobs require more steps than others, and thus some jobs take more clock pulses than others, because every step is driven by the clock. You'll also notice that the entire program is nothing but hexadecimal numbers. That's all it is. In fact, that's really all a microprocessor does, is manipulate numbers, right down to the single bit level. But if you can picture it, the program commands, or instructions, are in effect a unique number which turns on a specific utility circuit within the microprocessor. Now this is weird at first because we're used to speaking a language using letters and words and stuff, right? But surprisingly, you quickly find yourself speaking this programming language. This programming language is called machine code. Now, when I was learning microprocessors at college, we had a microprocessor training board, and you can see here it was just a hexadecimal keypad and a hexadecimal display. We had a sheet with all of the instructions and their hexadecimal numbers. But you quickly learned and memorized the numbers for the more common instructions. So as you write the program, you would want to instruct the processor to multiply, say, two numbers. The hexadecimal value for that command would be, say, hexadecimal AE. So you would enter AE into the program memory. So after a while of programming, you didn't even think, oh, multiply. You thought AE instinctively. Okay, I'm getting sidetracked. The bottom line is that machine code is really only numbers. And so even though we will be programming in words, those words get converted into these numbers. And you can see how the numbers actually function within the microprocessor.